Hello DB2 folks, this is the last video in chapter 11 in this exploration of sorting and grouping in relational database systems. It's time again to switch over from PostgreSQL to MonetDB. We have talked about sorting in MonetDB before, but let's revisit this here. Let's recall what we've seen back then, and let's add a few bits to the discussion here to round things off. All right, so if you recall, we were talking about sorting when we were talking about the 9th probe query. Okay, so I've built some playground data and query here to make all of this more concrete. What we will be talking now is a 2-column table sorted, and well, 2 columns A and S could potentially be sorting criteria. We have talked about the ordering of tables in MonetDB already, but back then we only looked at order by criteria that included a single column S, for example. We will revisit this here, and then later in the very final part of this video talk about the ordering of tables that is based on more than one criterion. For example, S and then column A. All right. So this will add a twist to all of this discussion. Right. But first off, of course, MonetDB buts, the binary association tables, they already provide ordered storage of rows. Okay, so if we are lucky, then indeed a but might already be sorted in just the order that our order by criteria request. Some order by queries will thus be no ops. MonetDB will be able to detect such situations because it maintains these tail properties, the properties sorted and reverse sorted, for example, that tell the system that the tail column of a particular but is already sorted, or maybe sorted in descending fashion, as is indicated by ref sorted. So yeah, we may be in luck, and sometimes ordering is indeed a no-op inside MonetDB's buts. Right. If this is not the case, and if indeed ordering has to be performed, then please recall that we introduced the order indexes, buts whose tail indeed indicate permutations of the rows of some other but, and applying these order indexes, these permutations of row positions to the target buts using algebra.projection would then lead to the desired row reordering. Okay, well, let's recall how this works. Okay, here is our input table, our sorted input table, of course represented in terms of 2 individual buts. This is the A but, all right, and these 2 columns, the head column and the S column, they make for the representation of the S column in our sorted table. Of course, both buts share the same head column here, the virtual head column. Both are aligned and synchronized on their head column. Okay. And ordering on the S column, a single criterion ordering on the S column, would be implemented by creating an order index for the S but. All right, this is exactly what I've indicated here. This is the order index of the S but. It's a permutation description, a permutation but, which is to be read like, well, the element that is currently located in the zeros row in the S but, in an ordered but, it would belong in the 6th row indeed. All right, so what's currently being found in the zeros row would indeed be placed in the 6th row if that would be an ordered but. All right. Okay, so let's see. So what's found in the 1st row in the unordered but would actually belong into the zeros row, in the very first position in an ordered but. So let's check. Indeed, this is the 0. The 0 is the smallest element in this S tail column. It would belong in the very first position if S were ordered. And let's see. Yes, so what's currently found in the 4th row of the unordered but, or the row with offset 4, would belong in the slot at offset 9 in the ordered but. So let's have a look. Well, 50 here is in the 4th slot. It would indeed belong into the last slot if S were ordered on ascending tail values. So this is this permutation but. And applying this permutation but to the S column would of course yield an ordered S column in ascending order. All right. Applying the same permutation but to the A but would of course lead to the corresponding A column that is ordered in ascending S fashion. So what we can see is that, for example, the row D30 indeed is now occurring in the ordered fashion. Of course, D and 30 are associated in the unordered input. They are associated in the ordered output. E and 50 are associated in the output because they have been associated in the input before. So a synchronized, a consistent application of this order index using algebra projection to all of the column buts leads to the complete ordered output that we were looking for. Okay. We have looked at the explain plans that are associated with such order by queries before. This is just to remind you that a query like this, a single criterion ordering that is applied to all of the columns of the sorted table, so that would be a 2-column output here, would be executed as follows. Well, we would of course access the but that represents the S column. We would apply the sorted but using algebra projection to make sure that only those rows in the S but are remaining that are currently visible. Okay, so once we've prepared this representation of the S but, we would then use algebra.sort. Algebra.sort to indeed perform the sorting on the S but. There is some argument bits here that you can pass to the algebra.sort. Well, should we sort in descending fashion? No. Will this be a stable sort? No. Shall we order the nil or null values in a particular fashion? No. Well, this is a vanilla sort on the S column. All right, so the output would be 3 output buts. We have discussed these 2 output buts before. Okay, so one of the output buts will indeed be the ordered S column. All right, but it's crucial that we also output the order index, because there might be other columns, the A column for example, that needs to undergo the same permutation of rows. We indeed need this order index output. It's indeed the crucial output of this algebra sort operation. There is a third output here that will come into play in a few moments. All right, well, we have the ordered S column already in hand. We also need the ordered A column. So what we do now is we access the original A column, still unsorted, but would then apply, well, visibility information and then the order information, the order index information that we've just computed to arrive at a column that contains A values in as sorted fashion. This is the semantics of this identifier here. It's the A column, but ordered according to the S values in ascending fashion. And of course, the sorted A column and the sorted S column both are assembled to deliver the final result of our sorting query. All right. Resorting the columns of a table again and again can be quite costly. And well, we have discussed already that the system has the opportunity to make the order indexes, the permutation butts, to make these persistent. All right. This is indeed what we request here. So please create an ordered index. Please create an order index, a permutation butt based on the S column of the sorted table. This would be made persistent and can then be reused to speed up the evaluation of the algebra sort operation. So if you look back at this particular operation, well, if there is already the order index on the SBUT available, then algebra sort has an easy job to do. It has no problem at all to generate this particular output, which would just be the application of the persistent order index onto the SBUT, and here it would just reproduce the persistent order index. Okay, so algebra sort would indeed benefit from such persistent order indexes. As we've already discussed too, these order indexes are indeed rather static structures. They are, as opposed to B+ trees, which were very dynamic and had some dedicated update and delete and insert maintenance routines. No such routines are available for order indexes. If an order index has indeed been created and the underlying base table, the sorted table in this case, would be updated, well, then there is actually only the option to throw away the order index and recreate it as needed, right? Or if that order index is indeed already persistent, we would insist that the underlying table is read-only and does not receive insert, updates, or deletes at all. If you think about it, an update, even a single row update on the underlying table, may lead to a rather heavy impact on the associated order index, and if we are out of luck, we would have to recreate the entire order index. That's why MonetDB currently opts to throw away the order indexes, the created order indexes, on a table update. So I invite you to maybe flip back to this slide, for example, and then think about what would happen if, say, this 10 value in the S column would be replaced by, say, 42. Okay, that's a local change in the SBUT, but it will be a non-local change in the associated order index. So I invite you to think about this, to compare this order index that we've seen here on the slide and the new order index that has to be created once you replace this 10 by 42 here. You will see that the impact will be non-local, and well, maybe you can think about what the general measure of the impact of such a single row update on the order index would be. Which rows in the order index would be affected, even though only a single cell here is changed in the underlying BUT. Okay, as I told you, algebra.sort can indeed make use of such order indexes. And why is this the case? Well, because there is the notion of tactical optimization inside MonetDB. Also a concept that we have talked about before, but let's revisit it here and let's recall what the tactical optimization indeed means. Well, even in the presence of an order index, what we will see when we look at the explain plan for a query that uses an order by, what we will see is just an application of algebra.sort. The explain plans would not explicitly access an order index or incorporate it into the mul statements that are employed to evaluate our SQL query. Instead, algebra.sort would internally check properties of the underlying BUT T that is to be sorted, and then decide using tactical optimization, which could be depicted like this decision tree here. It would use this decision tree internally to decide which algorithm to apply, which tactic to apply to arrive at a sorted T BUT. All right, maybe maybe the t-but is already sorted according to its tail column. Well, if this is the case, well, then this algebra.sort is indeed a no-op. Okay. Maybe the t-but is ref sorted, so it is sorted in descending order. If this algebra.sort is to produce a but in ascending order, well, then we can perform a reverse scan, a reverse memory scan of the tail values in the t-but to produce the desired output in ascending ordered fashion. And this again is something that would be much cheaper than the actual sorting operation. If this is not the case, then the next tactical decision would be this choice point, where we would look and see whether there is an order index available on T. Maybe a persistent order index has been created before. If this is the case, then algebra.sort can be simply implemented in the terms of algebra projection, in terms of a permutation of the rows of T. This is the third best option. If all else fails, then indeed we need to physically sort the rows of the input but T. MonetDB internally has an implementation of timsort, which is a rather recent modern version of an in-memory sort algorithm that is in some way a hybrid of a merge sort and an insertion sort that is aware of runs of values inside the base but T that are already sorted or that may be constant. So timsort is a rather advanced in-memory sorting algorithm that is then applied to enforce sort order. Timsort is also used in implementations of Python, for example. So it's a modern in-memory sorting algorithm that is suited to this particular task. All right, so let's switch over to MonetDB terminal and see how all of this plays together. Okay, so here we are. Right, as you can see, I have already started my MonetDB client here, and I'm currently talking normal SQL. And I do so because I would like to create the playground table first, our sorted table of 2 columns. All right, did that. And now I will insert a few values here. These are reminiscent of the values that you've already seen on the slides. Okay. And as we can see, it contains these S values here in a rather arbitrary unsorted fashion. Okay, 10 rows inserted. This is the state of our sorted table. Right. So now looking at the mal plan for a sorting query. Well, we have seen that before. Let's just revisit this. This would be the mal plan for our playground query or probe query. Let's scroll back here and see whether we can find the crucial bits. All right, indeed. So this is a query that asks for an ordering on the S column, and indeed the S column is what we first extract here. Well, we would then apply visibility information. Visibility information is available in the C5 but here. Once we've done that, it's time to indeed perform the algebra.sort. Okay, so the x24 but, this is all the visible S values. x24 is indeed the input to our algebra sort operation. All right. The other arguments are just these bits, these state bits that ask for descending or ascending sort order and so on. All right. What we get here is indeed the sorted SBUT and the order index that reflects the permutation that has been applied to the SBUT. Okay. Well, that's nice because we can use this order index later on once we've loaded the A column to also resort the values in the A but. Okay, so what you see here is that we load the A but. Its values are available in x8. So x8 is then the input to an algebra projection pass. So first apply visibility information and then apply the order index to arrive at an A column that's also sorted. All right, and well, this is all we need to then finally construct the final result of our query. Okay, what I've done here is if I switch over to this tab, Well, I've started MonetDB in the mode that we have used earlier, in the minus algorithm switch mode, in which all the technical decisions are made visible and are logged here in the MonetDB server console. You see it's currently idle because I'm not evaluating any queries, but lots of stuff has been dumped here already. Okay, so now if we switch back to our query terminal here, now that when we start to evaluate these queries, we should see in the server output what tactical decisions have been made by the operation, the mul operations. In particular, what tactical decisions have been made by algebra.sort. So let's evaluate this query once. And what you see here is, of course, the sorted AB output. All right, so sorted in S order here. All right. All right, so we see that indeed this query has been performed, and while this query was evaluated, there was indeed an invocation of the low-level but sort routine, which would be the low-level equivalent of the algebra.sort mul command. And well, nothing special has happened here. Indeed, but sort has decided to indeed use tim sort to indeed perform a physical sort, physical reorganization of the rows in the SPAT. And this took 133 microseconds. All right. So now let's evaluate this query again. Okay, same result here. And let's look at the terminal, at the tail of the output. What you can see here is that the system has indeed decided to create an order index, because it has detected that orderings of the S column appear to be part of the workload, of the system's workload, again and again. All right. So indeed it has created an order index. Indeed it has created such an order index before. The order index here, you can see that it indeed has been persisted. We invested some microseconds to persist this particular order index. All right. When we later check for the presence of this order index, we indeed find that it already been there. And when we then later have to perform sorts, well, then this sort, the algebra.sort and its low-level but sort routine internally will perform tactical optimization and then see that there is indeed an order index present. And well, in only 52 microseconds, which is just 1/3 of the time that we've used before, we can respond to the algebra.sort operation and very quickly establish S sort order as required. And well, from now on, if we repeat this particular query, we should see that indeed the order index is being reduced again and again. So only 36 microseconds in this particular case. Over time, the investment of creating and persisting the order index will pay off. Okay. Alternatively, well, we could have marked our table sorted as being read-only to avoid further updates, okay, and then create an explicit order index on this S column just to make sure that such an index is indeed present and that we can rely on the presence of this index even if the system has not decided on its own to create such an order index. So we could do that. And then, of course, if we look at the evaluation of this sort query again, we would see, let's scroll to the output, the tail of the output here. Oh, lots of stuff has happened. We should see that the order index has indeed been used here. Okay, right, so 145 microseconds. It's the first access to this particular order index. I think we can expect faster evaluations in subsequent invocations. Yes, all right. Caching effects observable here. All right. Okay, so much for that. Let's go back to the slide set. So now let's add one bit to this discussion of sorting in MonetDB. And this is multi-criteria order by. So all of the order by requests that we've seen so far have been on a single column, the single column S. Now I would like to extend that or generalize that and have a SQL query here that indeed uses two ordering criteria. And you know the semantics of such ordering criteria or lists of ordering criteria. What we will establish is a lexicographic ordering of the rows. We would first look at the S values of the rows. If the S values can already establish a sorting order, that's fine. But well, if the S values of the participating rows S1 and S2 they are called here, if they should be equal, well, then we would look at the A values to establish a sorting order. Only if these are equivalent to or equal to, then the sort order would be non-deterministic or undefined between the two rows S1 and S2. All right, so, but there is, of course, priority here. So S will be the first ordering criterion and only then A will be revisited. All right, so that appears to be tricky to implement using algebra.sort because algebra.sort only receives a single criterion, a single but that is to be sorted. So we need a generalization here, and I would only like to briefly discuss how MonetDB handles in this particular case. As we've already seen and what will become important now, algebra.sort indeed returns three result buts. It returns the ordered input S. Okay, we've seen that before. It returns the order index, which of course is crucial to also reorder other columns, the A column, for example. We have seen that. And it returns a third but G index, or the group index of S, as I call it here. This will be crucial to establish multi-criteria orderings. Okay, so let's see how this group index of column S looks like and how it's being used in such multi-criteria order by. All right, so this would be the SBUT, the original SBUT that is still unsorted, and we would feed this into our algebra.sort mul operation. Out of that come three output buts. We've only looked at the first two so far. This group index but is the new kid on the block. Of course, we would receive the ordered SBUT. As you can see here, everything has been ordered as expected. Tail value 0 at the beginning, tail value is 50 at the end here. Okay. This is the order index that we've already seen. Okay. And then this group index would indicate if there are repeating value groups inside this ordered SBUT. You see there is this repeating group of 50s and there's this repeating group of 10ths. These values do not provide a final ordering criterion in a situation where we have multiple criteria order by. So these rows agree in their S values. So another criterion has to decide, the A criterion in our sample query has to decide about the final overall ordering that has to be established. Okay, these repeating groups are encoded in this group index, but the third output of the algebra.sort. As you can see, this repeating group of 10s is reflected or represented by these OIDs 1 that are repeating here. The repeating group of 50s is represented by this repeating group of 5 OIDs here. Okay, so this is a representation of the repeating groups inside the ordered output. And well, it can be used to see where some refinement of the actual ordering has to be performed. Inside this group, inside such a group, we need to look at the A values to establish the final ordering. And this is the indicator that we need in the second stage of our sorting to perform the required refinement. Okay, so how would that refinement do work? Well, of course, we would first perform the algebra.sort on the S column. The S column is the primary ordering criterion and would be considered first here. This algebra.sort on the S column would have three outputs. Of course, the ordered S column itself and the order index. Both are not being displayed here on this particular slide and not considered any further. The third output of algebra.sort would be, well, the group index that we've just discussed. All right. We would use this group index together with the sorted A column. The A column is already sorted in S order, as you can see here. We would use that and feed this group index together with the ordered A column here. Well, the second ordering criterion. We would feed both of these into a variant of the algebra sort operation. I've called it algebra sort star here. It's indeed a variant of the algebra.sort operation in mul that can receive more than one input. It receives the input but to be sorted, and it also receives the group index or the index that contains the refinement information. So it's a variant of algebra.sort that receives two but arguments. Okay. Well, the repeating groups in our group index, they indicate that there is some reordering to be done. There's some reordering to be done inside these groups here. Right, the repeating groups are identified by the group index as but. Inside these groups, there is some reordering to be done, of course, based on the A values. All other rows are indicated by the group index as to be stable and unaffected by the refinement. There's no repeating values to be considered for this B value A. All of these are okay. There's no sorting to be done, but some resorting is to be done inside these indicated repeating groups. And this is performed. This resorting, this refinement inside these repeating groups, this is performed by this algebra sort star operation. And the outcome of this algebra sort star is, of course, a variant of an order index, as usual, as expected, as being is the output of an algebra.sort operation. In this case, this would be the output of the algebra.sort operation. And it's an order index that has been refined. All right. So as you can see, inside this repeating group, some reordering has been established. So inside these repeating groups, inside the offsets 1, 2, 3, indeed the order of the values has to be changed, right? Okay, so you see this is a local permutation inside this repeating group. Indeed, you'll find the same here. There is some reordering, some permutation to be done inside this repeating group. Okay, and this is a new order index that we could then apply to the to any column that is already been sorted by the S criterion. Okay, so to order a row by S, A, first to order a but by S, A, first order by S. We know how to do that using algebra.sort. Then compute algebra.sort star to arrive at this refinement, and then apply this refinement. Apply means use algebra projection to apply this particular refinement to the output of the ordering by S to obtain an ordering that is ordered by S first and by A second. Okay, so that would be the strategy to have a multi-column, multi-criteria order by in MonetDB. Okay, so let's see if we can indeed find this over on the MonetDB terminal. Let me prepare this here. Right, okay, there we go. There we are. So, right, this would be such an SQL query that indeed uses two ordering criteria, first S, then A, just as seen on the slides. And let's see how this looks when the mul plan is created by MonetDB. Okay, scroll back up to see the relevant bits. And as you can see, oh, indeed, there's two algebra sort operations involved. Okay, the first algebra sort operation is applied to x14, and if you have a closer look at x14, this is x14. This is just the S column that has already undergone the application of the visibility information. Okay, right. So this is the first sort according to the first criterion S. And what comes out of this is 3 buts. Okay. x17 is this group index, but it's used to perform the refinement. And as you can see in the second algebra.sort, indeed it's a algebra.sort variant, the sort star variant as it's been termed on the slides, a sort star variant that indeed also accepts the group index but as one additional but argument here. And it's this that particular a group index but that allows algebra.sort to output a refined order index. Okay, applying this refined order index x21 to the input columns of our query will produce an ordering that is first ordered by S and then ordered by column A. Okay, right, so two subsequent algebra.sort operations that are threaded together. The second receives input from the first to produce a refined order index. All right. Well, you can also play with this on the mul level of MonetDB. Let's do that as the final act in this particular video. Let's quit the SQL terminal here and activate a mul terminal. Now we are talking mul to MonetDB again. All right, and what we could do now is just to replay the essential bits of the plan that we have just seen, of a plan that first orders by S and then orders by A. So what we could do here is to initialize talking SQL with mul and then access the A column with visibility information of our sorted table, then access the S column with visibility information. Okay, so all the raw columns are now loaded, nothing has been sorted yet. What we would then do is to perform the first sorting of the S column, right? And what we would have as a temporary result here would be the already ordered S column. This is the already ordered S column, looks good to me, from 0 to 50 here. And of course we would also get the order index that will help us to reorder all other columns. There you have it, the order index. And we would receive the group index. We haven't seen such a group index before, but it's just the same as you've seen on the slides. You see the repeating groups here. 111 indicate the repeating group of tens. This indicates the repeating group of 50s in the S column. Okay. All right, this would now be fed into the second invocation of algebra.sort. All right, what you see here is that we would feed in the original A column and the order index on S. Using these two together, algebra.sort could create the S-ordered A column. All right, the S-ordered A column is already available. This would then be refined based on the group information or the group index information that we also pass into this algebra.sort. So let's do that. All right, this is the algebra.sort star operation that we've mentioned. Well, now we've got everything. We've got the refined ordering index that is indeed able to order by S first and by A second. This would just be applied to the original S and A columns. There we are. Well, and then we could just print the result here. And let's look, of course, the result would be ordered by the S column, this last column here first. So from 0 to 50 looks good to me. Inside such repeating S groups, we would find ascending A order. So F, H, I looks good to me. C, E, G, all right, looks good to me too. So that would be an S, A ordered output. Multiple ordering criteria implemented through a threaded, sequential implication of algebra.sort mul operators. Okay, so I think this concludes our discussion of sorting and grouping in PostgreSQL and MonetDB. Sorting and grouping are super relevant information operations, and as you have seen, sorting is really ubiquitous in the relation of SQL plans, not only for order by but also for distinct, joins, group by, and so on. All right, there's of course one other operation that is prevalent, that is super important in the relation of query relation plans in relational database systems, and that would be the join operation. Relational data design depends on the distribution of information in several tables. It's the task of queries to bring these tables together, to collect information from separate tables using join operations, to then well, produce query results that integrate data that has formerly been distributed. So join operations are at the core of every query relation engine in any relational database system, and joins are indeed on the table. They are in focus in our upcoming chapter 12. This is really important stuff in chapter 12, and I am looking forward to go through the material with you. But for now, let's call it a day. See you soon. Take care and bye-bye.